hope you can see me and you can hear me and you can even see the slides. So if it's okay, yeah. So thank you, Alejandro, for the presentation and also giving the opportunity to explain the facto progress. As coordinator of the project, I'm happy and really honored to be here and to explain the progress.
Eli,
so,
sorry, one suggestion, you can click maybe in ocultar in a way that this bar, yeah, exactly. And then it's perfect. Now it's perfect. Thank you.
Okay, sorry. Okay, so yes. Yeah, the title of my speech today is Speeding Up Battery Cell Manufacturing Through Modeling and Simulation. For those that doesn't know anything about the facto, it's a European H2020 funded project dealing with the modeling for manufacturing and cell design. So basically, we aim to go in detail, understand properly each of the individual process linked to the performance and aging, and somehow optimize the manufacturing through this modeling. But yeah, when we talk about speeding up, when through the de facto, we can see like from the holistic approach. So within the de facto project, we are dealing with the parametrization. So parametrization, because we have plenty of parameters to estimate, and somehow we aim to reduce the time and cost related to the experimental work to obtain or estimate these parameters. Also, one of the aims is to minimize the trial error approach by gaining more understanding on individual steps of manufacturing. Then obviously we have the cell, and the cell is degraded along the cycling, and we want to know more on this degradation mechanism so that later we can enhance cell performance. And also we want to optimize the cell design, and this should be done in an automatic way, linking to the manufacturing at least. So what we aim to do through the de facto projects is to rely on the multiphysics, because we are convinced the multiphysics model can answer all these aspects, speeding up the battery manufacturing. But then multiphysics models need to be accurate, robust, and also computationally efficient. Okay, so for today, I have prepared and divided the presentation into 4 topics. One is the parametrization, how models can contribute in the parametrization, improving or reducing the number of experiments to estimate the parameters. And then on the manufacturing process. And the third part of the presentation will be on the degradation mechanisms from the multi-scale approach. And then I will finalize the presentation just giving some information on how we are proceeding in the optimization loop to the optimizing cell design. So I will start with the parametrization and somehow models-based parametrization in a way that we propose to reduce the time and experimental work dealing with the parametrization. So within the facto project, we have around more than 10 models that will be developed within the whole project that, by the way, was started last year and will be running until 2023. And then we have models related to the manufacturing and also dealing with the performance and aging. And all of them has something in common, that they are multiphysics and they cover different scales. But they are multiphysics that require physicochemical parameters, and obviously you can rely on literature data. But if you have a particular chemistry, we are convinced that we have to go in detail and get insight on each individual parameters. So we have plenty of parameters. We make a calculation. Here you can see a draft estimation for each of the electrochemistry, the number of parameters that we would need to require. And looking at the electrochemical, for instance, we would need around 20 per electrode and chemistry. So it's a very tough and tedious work, and we are convinced that the models can help in reducing the time and experimental work here. So now I will show like 2 examples how we are dealing or how we are proposing models-based parametrization. Both are on the area of the continuum scale, but it gives an example of how we aim to work on facilitate the parametrization. So when we talk on the continuum scale, for instance, the P2T model, it requires electrolyte transport parameters. These are the 4 common transport parameters, like the ionic conductivity, transport number, electrolyte diffusion coefficient, and the thermodynamic factor. And within the factor, we have already taken measured by experimental methods, and what they have something different from each individual parameters is that we need a specific method and even a specific setup. So for instance, if we look to the ionic conductivity, we need to assemble symmetric stainless steel cells, and then we perform the EIS measurements. For the transport number, we have we need to assemble symmetric lithium-lithium cell, and we rely in Bruce-Vincent method. Basically, is a potentiostatic and combined potentiostatic to the EIS spectra. For the electrolyte diffusion coefficient, we need to have a symmetric lithium-lithium, but in this case, we run galvanostatic pulse relaxation, and then we get the electrolyte diffusion coefficient. And for the thermodynamic factor, we need to assemble 3 electrode configuration and perform the CV experiments. So basically, this required a huge amount of experiments. It's quite tedious and time consuming. So we aim here is to reduce the number of setups and optimize the testing methods. So, and this will be done by the models-based parametrization, as I was mentioning. So here we are focusing now on the electrolyte diffusivity estimation. From the experimental approach, as I said, we have to configure or assemble lithium-lithium cells, symmetrical cells, and then perform galvanostatic pulse relaxation. And from the relaxation, if we plot the logarithmic of the voltage, and then we get the slope of this figure, we can then later get the diffusivity. But for that, we need the transport number that we would rely on the Bruce-Vincent method. So this is quite tedious, and even if we, as we know, the electrolyte diffusion coefficients depend on the concentration, salt concentration, and on the temperature. So if we want to increase the number of values depending on these variables, the number of cells to be assembled would be huge, and it's quite time consuming. So what we are proposing here is to rely on reduce order models, and basically we believe in the reduce order models because in the end we need to solve an optimization problem. Optimization problems that basically wants to somehow minimize the error between the simulating voltage against the experimental voltage, and this is quite time consuming. So we need to have efficient codes or efficient models that mimics all the multiphysics, but then perform this algorithm optimization to later estimate the specific parameters. So we need to have the full model, then we build the reduced model, and we implement, for instance, like quasi optimization problems to first optimize the testing in order to evaluate and to get estimation of the parameters properly and efficiently and accurately. So for the case of the electrolyte diffusion estimation and the pulse relaxation method, this is the model for the concentration gradients within the separator and electrolyte. So this is the model that we usually discretize in finite element method in Python, thanks to the Phoenix library, and the simulation times takes around 10 seconds, which is not much, but then if you want to solve later the optimization, it might be huge. So here what we aim is we have already built these reduced order models. Basically, in the reduced order models, there are different ones, but here we have implement the preprocess one that basically relies on the P, O, D, and D PODEIM. POD stands for proper orthogonal decomposition. That basically what it starts from high dimensional systems and then projects the dynamics onto a lower dimensional systems. And the DEIM is used for the nonlinearity equations or nonlinearity correlations, which are here very important. So what we, in the pre-process state, what we need to run is like many simulations to get this snapshot and generate database. And then with this database, we somehow implement singular value decomposition. We obtain the representative modes, and later we analyze by POD and linearize by these methods. By doing this, we can reduce the computational cost from 10 seconds to only 1 second to solve exactly the same equation and to have exactly the same profiles of the concentration gradients. Later, once we have these reduced models, we want to solve the optimization problems, and here what we aim to do is to identify the equation that correlates the electrolyte diffusion coefficients together with the concentration. So in this case, we have taken into account this specific equation taken from the literature, and what we want to do is to identify the P1 and P2 parameters. So to obtain this P1 and P2, we need to solve this optimization. As I said, basically is minimizing the error between the simulated voltage against the experimental voltage, and the simulated voltage is obtained through the difference between the potential that is due to the lithium stripping and plating, and also due to the ionic potential difference due to the concentration gradient. So these are the equations. So once, and this is solved by BFDS method. So, yeah, and this is the P1 and P2. Yeah, and then this was the aim. And then what we've been doing is that we can run experiments, but we can run simulation with a synthetic test. So in this case, we took the literature data for the electrolyte coefficient diffusions, and we know which is the pattern issues follow, which is the blue line below the red one here. So this is the target. We need to identify exactly this pattern for the electrolyte diffusion coefficient. Therefore, what we do is identify the best testing condition so that for one test or one cell, we can identify properly the parameter. So in the end, we did in an iterative way. We make some obviously trials with different testing protocols, and then we came out with this specific test. Running this test, we came with exactly the same pattern, so we can see and we can say now that we are able to identify properly this parameter by using only one testing for a specific cell. And in this case, we would have the correlation between the electrolyte diffusion coefficient and the concentration. So we can say that we somehow identify the way to reduce the number of cells. And now something we are working on is that we want to extrapolate the estimation to other transport parameters like the ionic conductivity and transport number. So basically, in this sample, we took into account the relaxation, but for further new other parameters, we are also taking into account the pulse period. Now I will jump to the second case. And I'm happy that I also attend previous talk in the graphite silicon, because it's something we are working on, but at the continuum scale. So within the factor group, we have electrode that will be graphite and then composite with silicon. So here we have aimed to build this continuum scale model based on the P2D approach, but it has a new level. And this detailed model was basically developed in order to account the mechanical properties of the silicon, which might have much impact on the degradation as well. So here, this is the HCC half coin cell configuration with this graphite silicon. So we have already, we have the level 0 of the model, which is the typical equations of the P to D. Then we have the graphite. And then in the graphite, we have this lithium diffusion along the particle. And then we have the carbon matrix, that this is a representation of this carbon matrix. And inside, we have the silicon particle. So in the level 1, we will have the diffusion of the lithium along this carbon matrix. And then we have include the lithium exchange between the carbon and the silicon. And even we can include another level in which we consider the diffusion of the lithium along the silicon. So these are the results at different C rates, but considering the parameters from literature. So something we've been working on is that how to obtain these parameters for our specific case. So again, we rely on the electrochemical test, and we rely on the GITT experiments that basically we have used in the past to obtain the OCV and the solid diffusion coefficients. So here, instead of applying like analytical equation of the peak, we want to include the full model, but it's quite computational speak is quite expensive, and we need to somehow reduce or simplify the model. So here, what we have pursued is the following method. That first we have quantified the characteristic time of each individual mechanisms and compared to the characteristic time of the relaxation period in the GITT. Considering the results of the characteristic time, we have built a limiting model. And with these models, we have identified, or we have compared to the testing protocols. Then later again, we have implement quasi-neutron approach for optimization problem, and later we have estimated parameters. So here, what we did in here is to, as I said, calculate the characteristic time. And what we have is the time related to the relaxation with this black plateau line. So what first, it's worth to mention that what we want to obtain here is that we want to identify the dominating dynamics or mechanisms, so that we will be observing in the GITT experiments, because the fastest one we are not be able to identify, and then it doesn't have sense to include this into the limiting models to be using in the GITT optimization. So in this, if we look to this frame, we can see the following outcomes. That first, we have the orange line, and it's related to the diffusion in the carbon phase. What we see is larger than the relaxation time. So this means that this is the one is dominating, and we will be seen in the GITT. Then we have the red line, which is this one. And again, we have certain peak, a certain SOC. And in this case, it's something that we really also observing in the GITT, and it's dominating again. And then we have this blue line, is this one. It's related to the diffusion in the graphite, and it's a little bit under the relaxation time, so it's not, it will be faster, and we won't be able to see. And then we have the diffusion in the silicon, that it's much lower. And so when we say it's really fast, is there's no concentration gradients between the silicon, so we can avoid it, or we can skip it. So considering this, we have built these limiting models. And first, some assumption is that the potential, either ionic and electronic, and even the electrolyte diffusing concentration, we rely that doesn't vary significantly along the electrode thickness and during the relaxation. And then, as considering the characteristic time that we have obtained based on literature data that I didn't say, is that it's much smaller than the other, so there won't be any concentration gradients, and then we can assume it's plateau. So for the models, these limiting models, we account the diffusion of the lithium in the electrolyte, but this approximated by the spectral method just to run or to make it more efficiently. And then in the level 1, we will have carbon and graphite that is not taken into account, but also we have considered here. And then in here, we are taking into account the diffusion of the lithium in the particle, even the exchange between the carbon matrix and the silicon. And what we are eliminating in the limiting is the diffusion of the lithium along the silicon. So here again, we apply quasi-Newton approach to minimize the error or to identify the objective function and to certainly obtain the value of the diffusion constants. So what we basically what we did is in this case we assumed that there was a very fast kinetic between the silicon and the composite, so we were able to identify the diffusion coefficient. So this is an example how we used the models to improve the parametrization and therefore accelerate the experimental work. So yeah. And then now I'm jumping to the manufacturing process. It's another topic that we really dealing within the Facto. The idea obviously is to gain more understanding of each individual steps. So first, I would like to point out that within the Facto, we will have prototype cells, but also commercial cells that are developed in an industrial manufacturer, and then prototype cells that will be manufactured into research and universities. Also, something to take into account is the parameters from the processing. So what we aim here is how to monitor the data in the production line. We are now currently working in this field, and we are obviously the idea behind is that we need to have a very homogenized, we need to track or we need to monitor exactly the same parameter in the 3 facilities in order to then later compare the results and have a comparable results. So, and then we have this physicochemical and electrochemical characterization that provides insight on the products, which is basically the cell, but also in the intermediate phases or intermediate products of the manufacturing process. So we will be characterizing material, and then electrode, even electrolyte filling process is already being investigated through a specific setup. And then once with the cells and prototype cells, large cells, by the way, we will start running the aging tests soon. Yeah. Okay, so now coming to the modeling field. In the modeling, as I said, we want to gain more understanding on certain specific steps of the manufacturing. Basically, we will be concentrated on the electrode processing and also in the electrolyte filling process, which are one of the most critical ones. So for the electrode processes, we start from the slurry preparation, jump to the coating, and then calendering. And then once we have the cell assembly, we will deal with the electrolyte filling. So for the slurry preparation, we know that the carbon black agglomerates size distribution has a really high impact on the rheological properties of the slurry. So here, what we aim to do is to understand or to analyze the breakage of the carbon black agglomerates simulated by the CFD-DEM. So basically, we aim to predict the final agglomerate size distribution depending on the shear stress. And for the agglomerates, which are represented in the DEM, are represented by the primary particles connected to via breakable bonds. So within the unresolved CFD-DEM with laminar shear flow, what occurs is that drag force acting on the agglomerate leads to bond breakage, and this is provoking the smaller carbon black agglomerates. Then once we have this carbon black agglomerates size distribution fixed, we intend to go to the drying conditions, and then in here what we aim to do is study properly the effect of this drying condition on the structure formation. So for this, we need to rely on two different size scales. One is the unresolved CFD-DEM coupling, and then the other one is the resolved CFD-DEM coupling. Talking about the unresolved CFD-DEM, we aim to investigate the active material in the mesoscale or the carbon black at the microscales. From the resulting results, what we can say is that the simulation results mimics, or it's comparable to the experimental results, and it can be seen here. So for the result CFD-DEM coupling, basically we aim to investigate how the active material structure is formed at the microscale, and you can see some examples here of the single particle displacement, and then another sample of 8 particles in a cubic configuration displacement through the drying steps. So having this information in mind, later we can proceed with the optimization and validation. So now, okay. And then we jump to the calendaring. So once the microstructure is fixed, then we apply pressure to a plate. And then, so what we do is we use DEM models to investigate this calendaring process. And in here, we take into account the binder, which is represented by the interparticle bonds. And this is already included in the DEM. Also, adhesion to the current collector is included and is represented by the standard contact model. And also, effect of the heated calendar are also taken into account. Taking all this into account, we are later able to, again, optimize the calendaring step. Now, we proceed with the electrolyte cleaning process. I mean, once we have the electrode, then you need to proceed with several steps. And then once you build this, you assemble the cells, you need to fill with electrolyte. And this step, it's a very critical step, taking into account from the economical aspects and also electrochemical aspects. Economic and electrochemically talking about. So basically, it's because it's time consuming, and the wettability might impact also on the degradation of premature degradation of the cell. So within the factor, we will cover 2 scales and even different models to evaluate and to analyze the electrolyte filling process, starting from the mesoscale and then jumping to the cell level. So we will analyze pore level, electrode level, and then cell level as well. But here, what it's been shown here is based on the 2-phase flow using lattice Volmat's method. So basically, virtual electrodes are configured, and with these electrodes take into account is the active material with and without the binder. For this setup, the electrolyte properties mimics the propylene carbonate properties or parameters, and then the model itself is based on Shan-Shen approach. So basically, we want to evaluate the pressure gradient and also the saturation percentage, depending on certain parameters like the porosity, wetting behavior, and so on. So these are some of the results we have obtained within the factor. And basically here, what you can see is that when we increase the porosity, the pressure gradient goes lower, so facilitate the penetration, and even we can reach higher saturation percentage. in the same way that if we reduce the contact angle, or let's say we improve the wetting behavior, we obtain similar approach, that we reduce the pressure gradient between the two flows, and then we achieve higher saturation values. So also we have taken into account the binder wetting parameter on the contact angle of this binder. And here what you can see is that reducing this contact angle, we can certainly reduce the pressure gradient, but also there is certain shift from here in the zero that you can reach a higher saturation just without any pressure. And then again, we reached similar saturation percentage. And another outcome of the lattice-Boltzmann approach is that we can see the final state of the saturation, and here we can evaluate the gas entrapping. So depending on the porosity, it might have certain difference between the entrapping of the gas bubbling in the electrode. So with the highest porosity, apparently there's certain gas bubbling in the surface of the active material, while in the lower porosity regime, we see that the gas bubbles agglomerates are mainly in the pore structure. It's something really important, this issue, because as we know, the OEM requirements towards reducing the porosity, increasing the energy density. So obviously all these parameters are really important to track and to correlate to this manufacturing process. Yes, and now I jump to the third part. Basically, is gaining more understanding on the degradation mechanisms. And within the factor, we aim to solve this problem by the multi-scale approach, starting from atomistic, meso, and continuum. And basically, what we aim in the factor is to concentrate on the graphite silicon electrodes and mainly on the mechanical aspects of the silicon. So we know that this is something very important, the swelling of the silicon and how it's impacting on the structure of the graphite and even the SCI layer. So first, what we want to compute, and we have to start running a simulation at the atomistic level, and then what we came out with some values of the expansion, for instance, in the atomistic scale with the lithiation state. Also, we have applied certain pressure and see how the pressure is influencing, external pressure is influencing on the potential, but not on the volume. And then we have also analyzed the difference between crystalline silicon and amorphous silicon, because the bulk modulus are also completely different from one to the other. Then once we have these mechanical properties understood at the atomistic level, then we go to the mesoscale. So here we have two methods. One is the 3D resolve model. The other one is the DEM methods. So basically in the 3D resolve, we are coupling the electrochemical tool to the mechanical tool. And here again, the idea is to properly analyze the volume change with the SOC, also to gain more understanding on the stress and this how this stress is impacting on the degradation of the cell. And then obviously once we have this understanding, we'll be upscaled to the continuous scale where we will be running tests with the large cell configuration. So also, as I said, we have a different approach in the mesoscales. We have discrete element methods. Basically, we run simulation in order to, again, to understand properly mechanical and stress behavior depending on certain parameters. So these are the complementary work, but I think gives huge amount of information to the next scale, in which this is the cell level or continuous scale. So basically, we've been working on homogenizing the model to account the silicon carbon composite anodes. and then we can, and obviously this homogenization to the continuum somehow includes this phenomena, but simplifies it in a way that still is quite computationally efficient. And then also we go to the P4D approach, in which we take into account the large scales of the cell. And then I jump to the fourth part. I don't know how much time I have. Sorry, Alejandro, but yeah.
I think you have, yeah, you still have 10 minutes, including questions.
Okay, thank you. Okay, and the last part is about the optimizing the cell design. As I said, we again rely on the model-based optimization. And when we say optimization, we are dealing with the cell optimization, but also correlating cell parameters to the manufacturing parameters. So somehow we close the loop between the cell aging and manufacturing. So the method that we will be pursuing is the following one. We have the P4D model. With taking this into account, taking this as a baseline, we build the reduced models in two different approaches. One is the reduce order methods, and then the other one is a regressive model, SPGD, non-intrusive method. And then once we have these reduced models, we aim to build the optimization similar to the approach in the parametrization. But here we aim to identify obviously we will be doing some sensitivity analysis to identify the main or the critical parameters so that we can later can find the optimum or identify the ones that we should optimize, pursuing certain energy density or power density or cycle life, whatever. And then once we have this critical or identified the most important parameters, we will link to the manufacturing parameters. So far, we've been working on the reduced models, and as I said, we have two approaches. The one is based on the POD method, as that similar to the ones I presented previously, but the one I presented previously, it was pre-processed models. But then here we go further, and our reduced model is time adaptative. So the difference between both schemes is shown in here. So basically, when we need, at the beginning, the reduced model I presented was relying on many snapshots, and we need to build like a huge database. And then once we have this database, we build the reduced models by POD, DEM, and so on, and we run the simulation with the reduced model. Here, what we do is to combine or start. We can run experiments with this pre-processed data. Otherwise, if we don't have this data, we can just start running the full model. And once we have certain snapshots, we can jump to the reduced model. We build the reduced, and then we continue with the reduced model. In parallel, what we do is to measure the residuals and see if the error between the residual and the error between the reduced model and the full models is good enough or not. If not, we should jump to the full model, and then we continue with the full model until we have enough snapshot, and then with these snapshots readapt the reduced model. So this is something you can see here, because we already built the P2D model, the reduction of the P2D model. So here in blue, we start from the full model. At certain point, we jump to the reduced model, and we continue with the reduced until we need to jump to the full, apparently because the residuals are not good enough. Then we move again to the ROM, and then we continue like this. And obviously, this is something that reduces the computational cost substantially. And even though so far we have reduced it by a factor of 10, we expect to reduce much on the P4D model, in which we have much more information and much more database. Yeah. So, and this is like an example of there's no any difference between the results of the full model and the reduced models, and we can you can see any difference between both of them. And then we have the other option is basically we aim to here we develop a regression model. With this regression model, it's another way of simplifying the models. And then what we aim here is somehow combine the simulation results that basically comes from the raw model and then combine with experimental results. And we certainly build some hybrid twin models or hybrid models that will combine both aspects. So this is what we have done so far, but then we will be including these raw models into the optimization and further steps. So yeah, and with this, I would like to thank the whole consortium. We are 13 partners and we are doing a great job, I think. And as I said, we started last year, beginning of last year, and we'll go until middle of 2030. So thank you for your time, and I hope.
Thank you. Thank you very much, Elixabete, for a really nice overview of what is being done in de facto. So definitely a lot of synergies with Artistic, I think, a lot of way of collaborating, I find very, very nice. So, okay, we have several questions waiting for you, right, Fernando?
Yes, indeed. Let's start here with Jean, who will speak later, actually. So she asks the following. For the LVM filling model, what is the density ratio between the air phase and the liquid phase? If the ratio is high, would you mind to tell me more about the technique that you use to stabilize the model?
I think it's really interesting question, but I feel really sorry because I don't have the answer, as I'm not in charge of these models. Maybe what I could do is, if you write me an email, I could put you in contact with the people, by the way, is DLR, who is in charge of this activity.
Perfect. We have also a question from Abos here, from the artistic crowd. He asks, regarding the LVM model, how do you treat the CVD phase? Do you take into account nanoporosity inside the particle?
Yeah, I think it's already, I mean, it's not, maybe I didn't mention, but yeah, what I understand is that they have already taken into account, even, yes, they have also taken into account the nanoporosity. Yeah, this is already taken into account, but I could give you more details by email, but yeah.
Thank you for your answer. Here we have another question from Ezequiel Leiva, who asks, which force field do you use for your lithium silicon atomistic simulations?
I really feel very bad because again, I'm not in charge of the atomistic simulation. Anyway, I could put you in contact with the right person. Sorry for this.
No problem. Let's see. Here we have another question from G.R. Mueller. He asks, can you talk about the difference between crystalline and amorphous silicon behavior?
Yeah, what I understood what they did, but again, I'm not in charge of the atomistic scales, is that they evaluate the difference in the bulk modulus, and what they figured out is that there is a certain softening while shifting from crystalline to the amorphous phase.
I see. Thank you.
I think there are more questions in the chat, no?
Let's see. Let me check the chat right now.
I know it was question from
the same one from G.R.
Mueller.
Mueller. Yeah.
Okay.
Yeah,
Nice.
I think we have covered all the questions. Yes.
Thank you. I have one, Eli. So regarding this last part that you show, you talk about this hybrid twin, right? So this is, if I understood correctly, this is more for the aging part, or is for, let's say, everything you are doing in the project?
No, basically, yeah. In this work package, we aim to properly capture the aging part of the models capturing the aging of the cell rather than the whole compute. But then what we aim to somehow is the weak coupling. But as we will be figuring out which are the critical parameters where we aim to link to the manufacturing, but not we won't be building this hybrid twin for the manufacturing.
Okay, great. And for the first part of your talk, when you were talking about this parameter extraction for silicon graphite, with GITT and so on, so do you try also doing PITT, and I mean, to compare what you extract from the both techniques or something like that, or?
No, but it's something we are exploring, and we are trying to even taking into account. We now, as you could see, is that we would be able to extract only certain parameters, and now we are analyzing different methods to identify if these other mechanisms are dominated in these testing conditions. So PITT will be also considered. Very
interesting. And maybe a final question is about the electrolyte infiltration experiments, because you mentioned briefly that you are using, I don't remember which technique you mentioned, but you say that there is a setup being developed for characterizing electrolyte infiltration. Can you elaborate a little bit, if possible, about that, how you are doing that?
Yeah, I have to be honest that this is again something that the partner is performing. So okay. Yeah, again. Yes,
okay, no problem.
Put you in contact with the right person.
Okay, great. Well, I think Fernando, no more questions, no? In the
no,
chat?
We don't have more questions in the chat, neither in the question section. Yeah.
Well, Eddie, thank you very much for having accepted the invitation for your great talk today. So I would like to say that we are collaborating with Eddie. So we have a co-supervised PhD student, Marc Duquesnoy, who is also there. Marc spent 3 wonderful weeks working with Eli in San Sebastian in CDTech Energy Storage. So well, I want to say, Eli, that it's a great pleasure to work with you and with CDTech Energy Storage. A great honor. So thank you very much for everything, basically.
Yeah, thank you to you, and thank you for the invitation. It's a pleasure.
Thank you, Eddie.